In the deep past, the universe is without structure. Space itself is still stretching from its first great expansion, carrying with it the cooling glow of the cosmic microwave background. Temperatures fall, but not yet to the stillness of absolute zero. The young cosmos holds a soft afterheat, the fading warmth of its own birth. There is no familiar shape here, no disks, no spirals, no clusters, only a faintly mottled expanse of hydrogen and helium gas, seeded with the invisible presence of dark matter. These gases drift in patterns not yet visible, their densities slightly uneven like ripples left in a great ocean after a storm. The first stars will not come at once. For hundreds of millions of years, matter gathers almost in secret, guided by the gravity of the dark matter, halos, forming silently in the void. These halos have no light of their own, yet they are the quiet framework around which the future will take shape. They do not rush the process. Gravity works without haste, and the gas responds on cosmic timescales. Slowly, hydrogen clouds sink into the wells of invisible mass, their motions tangled at first, more like wandering than falling. Pressure rises in the densest knots, and the first small sparks of nuclear fusion ignite within them. These are population 3 stars, massive, short-lived, and unlike anything that will come later. They burn with a brightness that outshines entire galaxies to be, yet they live only for a moment in universal terms. Their ultraviolet light begins to pierce the darkness, breaking apart nearby hydrogen atoms in a process called ruinization, clearing pockets of space and allowing transparency where before there was haze. Ironically, this clarity also reveals the emptiness. The great reaches between the first luminous points are still vast and unfilled. The galaxies that will form from these first gatherings are not yet disks or spirals. They are irregular, chaotic assemblies of light and gas. Some collapse inward quickly, forming dense spheroids. Others stretch outward into uneven shapes like scattered grains caught in an unseen current. It will take the combination of mass, motion, and time to bring order to this scattered scene. That order will arrive slowly, almost imperceptibly, as the gravitational dance between matter and momentum begins to shape the gas into more defined forms. The earliest light is already telling the story of what will come. The radiation from the first stars enriches the surrounding gas with heavier elements when they end their lives in supernovae. These explosions are vast but fleeting matter thrown outward into the thin medium metals mixing with pristine hydrogen and helium. Every heavy atom that will later cool into dust, form into planets, or cycle through another star begins here in these brief violent moments. The irony is that this chaos is the seed of structure. Only through such disruption can the raw material for later stability be made. Over hundreds of millions of years, the young universe shifts from scattered brilliance to the first organized flows. Dark matter halos grow by merging their gravity wells deepening. Gas falls toward their centers sometimes too quickly, colliding and heating to the point where cooling becomes necessary before it can settle. In the places where cooling succeeds, gas begins to flatten, pulled into rotation by the conservation of angular momentum. The future spiral galaxies are still formless at this stage, but their rotation is set. Even now there is a quiet irony, though. These systems are among the most dynamic structures in the universe. Their motion is smooth, predictable, and patient, as though following instructions written long before stars were born. Telescopes peering back to this epoch see small compact galaxies, clumpy, irregular, glowing in shades of ultraviolet. Many will not survive unchanged. Mergers and collisions are the rule, not the exception. Yet through all of this, the same underlying process unfolds. Gravity gathers rotation, aligns, gas cools and settles. Eventually, some of these protogalaxies will acquire enough mass and stability for their gas to fall into a broad, rotating plane. This is the first suggestion of the disks to come. Seen from above, they would not yet resemble the graceful spirals of later ages. The arms are absent, the structure too turbulent. But the foundation is laid. The quiet truth is that spirals require patience, not only the conditions for rotation, but the time for patterns to emerge from that motion. In these earlier stages, the universe is still learning to draw them. This is also a time of extremes. Star formation rates are high in some regions, producing brilliant young clusters, while in others the gas remains untouched, waiting for its turn. In a way, the future beauty of spirals is being prepared by this unevenness, by the mixture of activity and stillness, that will later give rise to the contrast between arms and interarm spaces. Meanwhile, the expansion of the universe continues. On the larger scales, everything is moving apart, yet on smaller scales, gravity gathers matter together. This is one of the quiet contradictions of cosmic history, that in a universe defined by expansion, local structures can grow tighter, denser, and more intricate over time. Light from the first stars continues to travel outward, crossing billions of light years, some of it still in transit today. Those photons carry the story of the moment they left a record of the first ignition of fusion in a dark universe. They move steadily, unaffected by the passage of time, until they are intercepted by telescopes or absorbed by dust. Even here, in the earliest chapter of spiral galaxy history, dust is beginning to form from the debris of ancient supernova. This dust is both a veil and a canvas. It hides some of the light from view, yet it also provides the surfaces upon which new molecules can assemble. It is a reminder that the clarity of space is always partial, that light and shadow will share the same structures from the very start. And so, the scene is set. In the quiet depths, the raw material of spirals is already present. Hydrogen gas, dark matter halos, the first traces of heavier elements, and the rotation that will one day draw arms through the stars. But for now, the shapes are only hinted at. Time moves on without hurry. Gravity continues its work. The earliest galaxies begin to take forms that will echo across cosmic time, and though no spiral yet unfurls its arms, the future is written in the motion of the gas and the invisible skeleton of dark matter beneath it. The universe waits, holding the patterns that will one day turn darkness into disks of light. Gravity deepens its hold on the uneven sea of matter, and the first clumps that will become galaxies begin to feel the subtle push and pull of cosmic flows. These are not random drifts, but the slow, large-scale currents of structure formation filaments and nodes of the cosmic web, where dark matter strands converge and draw ordinary matter into their invisible embrace. Along these filaments, streams of hydrogen and helium glide toward the gathering points, their motions too vast and too gradual for any instant to be noticed. Over tens and hundreds of millions of years, these converging flows feed the growing halos of dark matter, swelling their mass and strengthening the gravitational wells at their centers. The gas within these wells is no longer free to drift. It falls inward, its paths bending into spirals under the influence of angular momentum, a motion inherited from the irregularities of its original collapse. In this turning, the future disk of a galaxy begins to take form not yet thin and graceful, but thick, turbulent, and hot. The particles of gas collide with one another, converting ordered motion into heat, and that heat must be radiated away before the gas can settle into a calmer, flatter structure. Cooling happens slowly, driven by the faint energy lost through atomic transitions. The irony is that this cooling so essential for structure is powered by the very atoms forged in the short, violent lives of the earlier stars. Without those heavier elements, the gas would remain stubbornly warm, unable to collapse further. As cooling continues, the gas sinks deeper into the gravitational potential, spreading outward into a rotating sheet. From a distance, it would appear as a dim, hazy disk surrounded by a halo of faintly glowing gas, all encased in the far larger and invisible cocoon of dark matter. The rotation of this disk is steady but uneven. Regions with higher density turn slightly faster, setting up the seeds of future instability. These seeds are the beginning of the great spirals, though they will not appear for hundreds of millions of years. The present form is more like a still pond with barely perceptible ripples, the smoothness hiding the patterns that will later be traced in starlight. Around the young disk, other small galaxies drift in the same gravitational environment. Some will be captured and consumed, their stars scattered into the halo, their gas folded into the disk. Others will pass just close enough to tug at the structure, altering its rotation and redistributing its mass. These early interactions are quiet compared to the grand mergers of later cosmic history, yet their influence is lasting. A close passage can shift the entire orientation of the disk, tilt its plane, or thicken its structure with fresh infall. Meanwhile, the inner regions of the galaxy to be grow denser, and the central bulge begins to emerge, not yet a fully distinct feature, but a swelling of the star field at the heart of the system. Here stars form rapidly from collapsing gas clouds, their orbits more random than the ordered motion of the disk. Many of these central stars are old by cosmic standards, their light already mellowed to a softer hue. They serve as a stable core around which the rest of the galaxy will turn a gravitational anchor that resists the distortions of later encounters. In the outer disk, conditions vary from place to place. Some regions are rich in gas, forming clusters of bright young stars, while others remain dark and quiet. The interplay between these regions sets the stage for future contrasts, arms and gaps, brightness and shadow. It is here in the difference between the active and the still that the eventual spiral structure will find its strongest expression. The dark matter halo that encloses the entire system is still growing. Streams of matter continue to fall in from the cosmic web, delivering both gas and smaller dark matter clumps. These additions subtly alter the rotation curve of the galaxy, maintaining the flatness that will later puzzle astronomers who do not yet know of the halo's presence. This unseen scaffolding holds the disk together against the centrifugal pull of its own rotation, allowing the spiral pattern to one day persist without winding tightly into nothing. Cooling gas in the disk begins to settle into thinner layers. With each rotation, the turbulence lessens and the sheet becomes more ordered. Star formation rises and falls in gentle cycles governed by the supply of dense cold gas. There is a quiet irony in the fact that the very process of star formation consumes the fuel that makes it possible, ensuring that the galaxy's brightest periods are temporary. In time, these cycles will imprint themselves on the spiral arms regions of dense gas feeding new stars, followed by aging clusters drifting into the interarm spaces. The earliest hints of this process are already here, though the patterns are still crude, more mottled than organized. If one could look from above, the disk might show faint irregular arcs, proto-arms shaped by the rotation and by small variations in density. They are not yet the smooth, continuous curves of a mature spiral galaxy, but they are the first suggestion that such order is possible. These arcs persist not because the same stars remain in them, but because the pattern itself is a wave moving through the disk. The stars are passengers drifting in and out while the wave maintains its form. This principle, still centuries from being understood by human science, is already in quiet operation here. Beyond the boundaries of the young galaxy, the night of the universe is not truly dark. Other galaxies are forming along the filaments, their light faint with distance, but steadily increasing as more stars ignite. The background glow grows richer, filled with points of light that are themselves entire systems. Each one has its own history of collapse, cooling, and rotation, its own balance of order and turbulence. Some will become spirals, others will take different forms, but all are shaped by the same interplay between gravity, gas, and time. In the young spiral's disk, dust is becoming more common. Formed in the atmospheres of dying stars and expelled in supernovae, it absorbs and scatters light, tracing the lanes that will later become the dark rivers dividing the spiral arms. Even now these lanes hint at a structure that does not yet exist in full, a future map of where stars will be born and where they will fade. The dust also cools the gas by providing surfaces for molecules to form, especially molecular hydrogen, which radiates heat efficiently. This cooling is essential for the creation of the dense clouds that collapse into new stars. Without it, the galaxy's star formation would stall, and the spiral arms, when they arrive, would be fainter and shorter-lived. The balance of processes cooling star formation, enrichment, and inflow sets the long-term character of the galaxy. It is a balance that can be disturbed by encounters or altered by the gradual depletion of gas. But for now, in this early phase, the flows are steady enough to allow the disk to grow and flatten to turn with quiet persistence. The first full rotation of the galaxy's outer edge may take hundreds of millions of years, yet each turn adds to the shaping of the pattern. The seeds of the future spiral are here: a rotating disk, a central bulge, a supply of gas and dust, and the gravitational frame of dark matter. The arms themselves are still only potential, waiting for the right combination of density, rotation, and time. In the silence of the early universe, the galaxy spins on, holding its future in its motion. Over time, the young disk settles into a smoother rotation, its turbulence fading as energy is radiated away, and gas sinks toward the midplane. What was once a thick, uneven structure now thins, stretching outward into a broad, luminous sheet. The galaxy has learned to turn in rhythm, each star and cloud following its own path, yet all bound together by the same gravitational script. It is in this patient turning that the first true spiral forms will begin to take shape, though they emerge not as sudden creations but as gradual patterns drawn out over hundreds of millions of years. Small instabilities, regions slightly denser than their surroundings, start to amplify as they orbit. Gas flows into these denser zones, compressing and cooling, triggering bursts of star formation. The youngest stars, massive and blue, burn with an intensity that marks these regions clearly against the softer background of older, redder stars. From above, these clusters would seem like bright beacons tracing arcs through the disk, faint at first, but increasingly distinct as the pattern repeats and strengthens. The arms are not solid structures, nor are they made of the same stars over time. Instead, they are density waves, a kind of moving traffic jam where matter flows in and out, piling up briefly before moving on. The irony is that while the stars give the arms their shape in visible light, it is the gas cooled dark and nearly invisible that sustains them, for only in the arms does the compression become great enough to birth new generations of stars. Between the arms, the disk is quieter, with older stars drifting in a looser arrangement. Here the interarm regions act as vast archives holding stars that were once in arms but have since moved away their orbits, carrying them into the calmer stretches of the disk. The overall motion is deceptively simple. Each star orbits the centre under the pull of gravity, yet the speed is such that stars near the outer edges keep pace with those closer to the centre, a flat rotation curve made possible by the dark matter halo. Without this invisible framework, the spiral structure would quickly wind too tightly to persist, losing its form in a mere fraction of cosmic history. As the pattern grows clearer, dust lanes appear alongside the bright arcs marking the places where gas clouds are thickest. These lanes are cold compared to the stars they obscure, yet they are nurseries sheltering the molecular clouds that will eventually collapse into new suns. The interplay between brightness and darkness becomes a defining feature of the spiral light marking the newborn stars shadow marking the material for those yet to come. From within the disk, these lanes would appear as vast, looming curtains against the pale shimmer of the star field, shifting only with the slow motion of the galaxy's rotation. The central bulge continues to evolve its population of stars, aging together their orbits, crossing in a random spheroidal swarm. Unlike the ordered rotation of the disk, the bulge holds a memory of the galaxy's more chaotic beginnings, a reminder of the turbulent collapses and mergers that preceded the spiral's formation. Here in the bulge, time seems to pass differently. New star formation is rare, and change comes not from birth, but from the slow dimming of ancient light. Meanwhile, the outer disk expands, fed by the continued infall of gas from the surrounding halo and the cosmic web beyond. These inflows are not constant streams, but irregular deliveries arriving in filaments and clouds that sometimes collide with the disk at oblique angles, stirring ripples through the spiral pattern. Some of these encounters are subtle, altering the arms only slightly. Others can set off waves that ripple through the entire structure, enhancing its contrast and triggering fresh star formation far from the center. Occasionally, a small satellite galaxy passes close enough to leave a lasting mark, pulling at the arms and creating asymmetries. These interactions are quiet on human timescales, unfolding over tens of millions of years, yet they are enough to shape the spiral into forms that differ from perfect symmetry. One arm slightly longer, another more tightly wound. The beauty of these imperfections is that they make the galaxy's structure unique, a singular arrangement of light and matter in the vast expanse. In the arms themselves, life cycles of stars play out quickly. Massive stars live fast and die young, ending their lives in supernova explosions that scatter heavier elements back into the gas, enriching it for future generations. Smaller stars live for billions of years, moving gradually away from the arms into the interarm spaces where they will drift until the galaxy itself changes form. The enrichment process is slow but transformative. With each cycle, the proportion of heavier elements in the gas grows, making possible the formation of more complex molecules and in the far future planetary systems. The arms are thus not only patterns of light but engines of chemical evolution, drawing in fresh gas and returning it altered to the galaxy's circulation. Beyond the disk, the dark matter halo remains the silent guardian of this process, its mass holding the system together while remaining unseen. Its extent is far greater than the luminous part of the galaxy, and its particles pass through the disk without interacting with the stars or gas, their influence felt only through gravity. Without this vast halo, the arms would lose coherence, the disk would fly apart, and the spiral's delicate balance between rotation and self-gravity would collapse. Even as the galaxy turns the universe around, it changes. Other galaxies grow brighter, some forming their own spirals, others becoming irregular or elliptical through mergers. The filaments of the cosmic web continue to feed the clusters, where galaxies gather, and the spaces between them grow emptier as matter falls inward. The spiral is both participant in and witness to this larger flow, its form shaped by forces on scales far beyond its own disk. Inside, the rhythm of star formation continues, neither rushed nor stagnant. Arms sweep slowly through the disk, carrying with them the spark of new light and the shadow of dust. The pattern they create is not permanent, yet it can last for billions of years, sustained by the balance of density waves and fresh infall of gas. Over time, the spiral will change, arms may fade or fragment gas may be used up, but for now, in this long middle phase, it holds its form with quiet persistence. To an observer far above the galactic plane, the sight would be one of understated grandeur. Two or more arms winding gracefully from a bright central bulge, their curves traced in blue-white clusters and dark lanes, all set against the faint glow of the outer disk. The galaxy turns in silence, its motion too slow to see, yet its structure too deliberate to be the product of chance. This is the stage where the spiral is both most alive and most stable, a moment in cosmic history when light and motion are in near-perfect balance. It will not remain so forever, but the stars do not measure time as humans do, and the galaxy's long spiral dance will continue far beyond the span of any single observer. The first spirals unfurl without a single moment of beginning their arcs, emerging gradually from the smooth turning of the galactic disk. At first they are faint, only slight variations in brightness and density, but over millions of years they grow sharper, drawn out by the steady pull of rotation and the rhythmic passage of density waves. Gas clouds drifting through the disk encounter these waves, and slow, compressed by their gravity into narrower, denser lanes. In these compressed regions, the pressure rises, molecules form, and stars are born in bursts that light the spiral arms with clusters of blue-white brilliance. The younger stars burn fiercely and briefly, so the arms are marked not only by their brightness, but by their transience regions of constant renewal, where each generation of stars fades and is replaced before the spiral loses its shape. Between the arms, the older stars drift more widely, their light cooler and steadier, filling the interarm regions with a diffuse glow. The dust and gas that weave through the arms create striking contrasts, dark lanes that twist alongside the luminous arcs. These dust lanes are not empty, but rich in potential, holding the raw material for future star formation. Their shadows are the promise of light yet to come, and their placement just ahead of the brightest clusters, relative to the galaxy's rotation, reveals the timing of the wave's passage. In this arrangement, the spiral is not a fixed object, but a pattern in motion, its components constantly changing, yet its form enduring. The galaxy's rotation is nearly flat, the outer stars keeping pace with those much nearer to the centre, an effect made possible by the presence of the unseen dark matter halo. Without this hidden mass, the arms would twist more tightly with every turn, eventually vanishing into disorder. Instead, the pattern persists, its scale maintained over vast stretches of time. As the arms sweep through the disk, they shape the life cycle of the galaxy. Star formation follows their path, and the enriched gas from dying stars returns to the interstellar medium, feeding the next generation. Each passage of the arms is both an ending and a beginning, each turn layering the galaxy with new structures and subtle changes in composition. Over hundreds of millions of years, the spiral becomes more defined, its arms longer, its curves smoother. Yet the process is never complete. Small irregularities remain the result of gravitational nudges from nearby systems, or uneven flows of gas from the halo. These irregularities can split an arm into fragments, or cause it to branch, adding complexity to the pattern, without disrupting its overall coherence. Occasionally the disk feels the influence of a passing satellite galaxy. Even without a direct collision, the tidal forces from such an encounter can draw out or tighten the arms, changing their pitch angle and altering the distribution of stars and gas. These events are slow, unfolding over spans so long that the galaxy has time to adjust, incorporating the changes into its ongoing motion. The central bulge, dense with older stars, remains steady through these alterations, serving as a fixed point around which the spiral's elegance turns. The bulge's population is largely quiescent, the stars within it moving in random orbits, their light softening over time. Though new stars rarely form here, the bulge holds the memory of the galaxy's earliest assembly, its density a relic of the chaotic mergers and collapses that preceded the disk's ordered rotation. In the outer regions of the galaxy, the spiral arms grow fainter, their structure less defined. Here the density waves are weaker, the gas thinner, and star formation more sporadic. The outer disk is a quiet realm, yet it plays an important role as a reservoir, its sparse gas eventually drawn inward by gravitational interactions feeding the brighter, more active inner arms. The boundary between the disk and the halo is not sharp. Stars can be found far above and below the plane, some kicked out of the disk by past encounters or supernova explosions. These stars tracing long tilted orbits are reminders that even in a structure as ordered as a spiral galaxy, there is room for motion beyond the main rotation. The interplay between gas stars and dust continues without pause. Supernovae in the arms send shock waves into the surrounding gas, triggering new star formation in some places while dispersing clouds in others. Massive stars, even before they die, shape their environments through stellar winds, carving bubbles and cavities that alter the flow of matter. The result is a texture within the arms regions of intense activity, interwoven with patches of relative calm. Viewed from far above, these variations give the spiral a living quality, its form both constant in outline and endlessly changing in detail. Over time, the chemical composition of the galaxy shifts. With each cycle of star birth and death, the interstellar medium grows richer in elements heavier than helium. These metals are essential for the cooling of gas and for the eventual formation of planets around later generation stars. The spiral arms, by concentrating and recycling this material, serve as the engines of this gradual enrichment. Even as they shape the galaxy's light, they are also writing its chemical history one rotation at a time. Beyond the galaxy, the universe is busy with its own transformations. Other spirals form along the filaments of the cosmic web, their arms winding in various degrees of tightness, depending on their rotation speeds and mass distributions. Ellipticals swell from mergers, irregulars scatter their light unevenly across the sky, and clusters of galaxies assemble into larger structures. The spiral in focus here is only one participant in this larger choreography, yet within its own boundaries it holds a complete narrative of order rising from chaos. In its symmetry there is still imperfection, in its regularity there is constant change, and in its beauty there is the quiet inevitability of transformation. The spiral arms will not last forever. Their maintenance depends on the ongoing inflow of gas, the balance of rotation, and the persistence of the density wave pattern. Over billions of years, as the gas supply diminishes, the arms will fade their outlines, softening into the smoother profile of a lenticular galaxy. But that end lies far in the future. For now the arms continue their patient sweep each turn, an affirmation of the balance between gravity's pull and motion's resistance, between light's brief blaze and shadow's long persistence. In the stillness of cosmic time, the spiral's unfurling is both a momentary pattern and a structure enduring across eons, a reminder that the universe shapes beauty not in sudden acts, but in the slow, unbroken work of rotation and light. Within the spiral arms, star formation is at its most vigorous. Dense molecular clouds, cooled by the shielding effect of dust collapse under their own gravity, fragmenting into clusters of newborn stars. The most massive among them ignite almost instantly their ultraviolet radiation, and stellar winds beginning to sculpt the very clouds from which they emerged. These giants live for only a few million years, a blink against the galaxy's vast timeline, yet they dominate the arm's brightness. Their light spills across the surrounding space, illuminating nearby dust lanes and making the contrast between light and shadow even more pronounced. Supernovae follow in quick succession, each explosion sending shock waves through the interstellar medium, compressing some clouds into new star-forming regions while dispersing others entirely. This constant cycle of creation and destruction sustains the arm's vivid appearance. Even so, the individual stars within them are always moving on, drifting away into the interarm regions. Between the arms, the scene is quieter. Older stars shine with a steady, softer glow, their orbits carrying them slowly around the galaxy, largely unaffected by the starburst activity elsewhere. Here the gas is thinner, and the dust is more diffuse, offering fewer opportunities for new star formation. The difference between the busy luminous arms and these subdued stretches is one of the most striking features of a spiral galaxy. From a great distance, this contrast creates the clean, graceful curves of the spiral pattern. Up close, it reveals a far more complex interplay of forces. Dust lanes winding alongside the arms act as signposts of where density waves are at work. They appear dark in visible light but are alive with activity at other wavelengths, glowing faintly in the infrared from the warmth of hidden young stars. Their position just upstream of the brightest star clusters is no accident. The gas enters the denser region of the wave, first is compressed, and then a short distance later in its orbit gives rise to star formation. This spatial offset, subtle but measurable, is one of the quiet indicators of the galaxy's deeper mechanics. The rotation of the disk remains steady, and its flat velocity curve continues to defy the expectations set by visible mass alone. Dark matter unseen yet indispensable holds the structure together, ensuring that the arms do not wind themselves into oblivion. Its halo extends far beyond the luminous disk, influencing the motion of stars at every radius. Without it, the balance between rotation and gravity would collapse, and the spiral's elegance would be short-lived. The bulge at the center continues its slow evolution. The stars there are old, their light golden and diffuse, spread across orbits that have long since lost any common direction. The bulge is less a site of creation than a record of what came before the remnant of the galaxy's earliest and most chaotic phase, when collisions and rapid starbursts dominated. Its dense gravitational field anchors the inner ends of the arms, providing a stable hub from which they unwind. Farther out, the outer disk stretches toward the faint edge of the galaxy's influence. Here the spiral arms lose some of their coherence, breaking into fragments and fading into a halo of scattered stars and gas. In these outer reaches, gravitational stability is weaker, and tidal interactions with small companion galaxies can create warps or asymmetries. Some of these companions are slowly being drawn in their gas streams, arcing toward the disk, feeding fresh material into the spiral structure. These infalls are irregular but essential, replenishing the gas supply that would otherwise be consumed by continuous star formation. Every encounter leaves a mark. A passing dwarf galaxy might pull one arm outward, lengthening its curve, or it might drive waves of compression through the disk, triggering bursts of star formation far from the center. Though these events play out over hundreds of millions of years, they subtly reshape the spiral's geometry, ensuring that no two rotations are identical. This slow variability is one of the ironies of galactic structure. What appears from afar to be timeless symmetry is in fact a dynamic, ever-changing arrangement. Within the arm's feedback from massive stars continues to shape the interstellar medium. Stellar winds carve cavities, ultraviolet radiation strips electrons from atoms, and supernovae distribute heavy elements across vast regions. These processes enrich the galaxy's gas with carbon-oxygen ion and countless other elements, each one destined to cycle through future generations of stars. Over billions of years, this gradual enrichment changes the character of the galaxy's star formation, allowing for cooler clouds, more efficient collapse, and eventually the formation of planets. The spiral arms are in this sense both the architects of the galaxy's appearance and the engines of its chemical evolution. From above, the spiral's beauty lies in its geometry. From within, its significance lies in its ability to transform raw gas into stars and then recycle their remains into ever more complex matter. Beyond the visible disk, the dark matter halo remains indifferent to these internal processes. Its role is structural, not chemical, and it exerts its influence through gravity alone. It does not shine, it does not absorb or scatter light, but without it the spiral's cohesion would unravel. The halo also extends the galaxy's gravitational reach, allowing it to gather and retain material from its surroundings. Small streams of gas from the intergalactic medium continue to slip into the outer disk invisible in optical light, but detectable in the faint radio emission of neutral hydrogen. These quiet inflows are as important to the spiral's longevity as the dramatic bursts of star formation within its arms. The galaxy's rotation carries it through these cycles endlessly. Arms sweep around, star formation ignites and fades, dust forms and disperses, and the chemical makeup of the interstellar medium shifts ever so slightly with each turn. To a human perspective, the spiral's form appears eternal, but on cosmic timescales it is an evolving structure, its present state only one chapter in a long and continuous transformation. The arms that exist now will not be the same in 1 billion years. Their stars will have drifted away, their gas will have moved on, and their pattern will have shifted under the influence of internal dynamics and external encounters. Yet the spiral itself as a concept and a pattern will persist as long as the conditions of rotation, density and gas supply are met. In this way, the spiral is less an object than a process, a sustained interplay of matter and motion that gives rise to the illusion of permanence. From the calm outskirts to the turbulent arms, from the quiet bulge to the unseen halo, every part of the galaxy contributes to this ongoing creation. Each turn of the disk is both repetition and change, a slow, unending dance that shapes the galaxy's light structure and future. And so the spiral continues its arms winding outward in luminous arcs, a patient expression of the universe's ability to turn chaos into order, without haste, without rest. Encasing the entire spiral galaxy as a structure that never appears in visible light, yet governs much of what the luminous matter within can do the dark matter halo. It stretches far beyond the edge of the disk, an invisible sphere, whose mass outweighs all the stars' gas and dust combined. Its particles pass through ordinary matter without interacting except through gravity, and yet it is this gravity that flattens the galaxy's rotation curve, allowing stars at the edge to orbit almost as swiftly as those near the center. Without this stabilizing frame, the spiral arms would wind themselves tighter, with each rotation eventually erasing their graceful curves. Instead, the arms persist patterns of density moving through the disk like slow galactic tides. The halo does not sit motionless. It grows as the galaxy accretes more matter from its surroundings, drawing in diffuse hydrogen from the cosmic web, and sometimes swallowing smaller dark matter clumps along with their stars. This growth is uneven, shaped by the larger-scale flows of the universe, where filaments of matter feed into denser knots and clusters. Along these filaments, streams of cold gas travel for millions of light years before being captured by the galaxy's gravity, slipping into the halo and eventually spiraling down toward the disk. These infalling streams are among the galaxy's most important lifelines. Without them, the gas in the disk would gradually be consumed by star formation, leaving the spiral arms to fade into pale outlines. The streams arrive in delicate filaments, sometimes breaking into clouds that orbit for hundreds of millions of years before finally merging with the disk. When they do, their motion often differs from the rotation of the galaxy, creating subtle ripples or warps in the outer regions. Some of these distortions are smoothed away over time. Others become long-lived features that slightly bend the symmetry of the arms. The halo also acts as a shield. While galaxies occasionally collide more often, they pass near one another, their halos overlapping long before their disks make contact. In these encounters, the outer halo absorbs some of the gravitational strain, preventing the central structure from being too violently disrupted. The halo's mass can deflect or capture small companions, stripping them of their gas and stars before they ever reach the disk. This quiet protection means that while the spiral galaxy may be reshaped by its environment, it is rarely destroyed by it during this long middle stage of its life. Within the disk, the presence of the halo shapes not only the rotation, but also the stability of the spiral arms. The density waves rely on the balance between self-gravity and the restoring force of rotation. The halo's mass distribution keeps this balance in a range where the pattern can persist for billions of years. This is not a fixed relationship. The halo slowly evolves as it gains mass and as its density profile shifts, but its effect is to maintain the conditions that allow the spiral form to endure. The dark matter itself remains a mystery. No light reflects from it, no absorption lines mark its presence, and no particle has yet been directly detected. Its reality is inferred from the motions of stars, from the bending of light in gravitational lensing, and from the patterns of cosmic structure on the larger scales. The irony is that while invisible, it is the most massive component of the galaxy, the hidden architect of its form and longevity. The ordinary matter with all its light and colour is merely the tracer of the deeper gravitational landscape carved by the halo. In the spiral arms, star formation continues to cycle, but the rate is influenced by the availability of gas drawn in from the halo. Some infalling material arrives enriched by previous generations of stars in small satellite galaxies, adding to the metallicity of the disk. Other streams are nearly pristine hydrogen and helium, diluting the chemical abundance and altering the cooling rates of the interstellar medium. This mixture shapes the kinds of stars that form the pace of their birth and the texture of the arms themselves. Over time, the accumulation of heavier elements in the disk becomes more pronounced near the center, where star formation has been most intense for the longest period. This creates a gradient in metallicity, with the outer regions remaining more primitive in composition. It is a gradient carried forward with each new rotation subtly altering the colors of the arms and the spectrum of light the galaxy sends into the void. The halo also serves as a record of the galaxy's past. Stars and gas from long-absorbed companions drift in its outer reaches, forming faint streams that wrap around the galaxy like ghostly ribbons. These tidal streams move slowly, taking billions of years to mix completely into the halo's smooth background. Some will eventually fall inward, their stars joining the disk, or bulge their gas-feeding new star formation. Others will remain in the halo indefinitely, their paths stable enough to persist, until the galaxy itself changes form. On rare occasions, the halo channels in a satellite galaxy that survives long enough to plunge through the disk. The impact can set off a cascade of events. Density waves amplify star formation surges, and the arms grow brighter and more irregular. The halo's role in such events is twofold. It delivers the companion, and it softens the blow by absorbing some of the orbital energy, slowing the merger. These interactions are part of the ongoing dialogue between the halo and the luminous disk, a dialogue measured not in words but in orbital shifts, warps, and bursts of light. From the perspective of the spiral galaxy as a whole, the halo's most important gift is time. By stabilizing the rotation and feeding the disk, it allows the spiral pattern to last far longer than it would in isolation. Without this support, the galaxy would exhaust its gas more quickly, and the arms would dissolve into a featureless disk. Instead, the spiral remains in its long middle age, a structure maintained by the continuous exchange between visible and invisible matter. Beyond the halo's edge lies the deep intergalactic dark, punctuated by the faint glow of distant galaxies along the cosmic web. Here, the scale of the halo is matched only by the scale of the structures it connects, to a reminder that no galaxy is truly alone, and that the flows of matter and gravity extend far beyond what light can show. The spiral's halo is just one thread in a vast interconnected tapestry, its invisible presence shaping both the life of the galaxy it holds and the cosmic environment it inhabits. Inside the disk, the arms wind on indifferent to the halo's invisibility, responding only to the gravitational conditions it sets. The dust lanes continue to trace the regions of compression. The blue-white clusters continue to mark the latest wave of starbirth, and the older stars in the interarm regions continue their steady orbits. The visible and invisible remain intertwined, each shaping the other, each incomplete without the other's presence. In this balance, the spiral endures bright in its disk, dark in its halo, turning slowly through a universe that both feeds and confines it. The spiral arms that sweep through the galaxy's disk are not static pathways, but living structures changing subtly with every rotation. They are sustained by the motion of countless stars, yet the stars themselves are only temporary residents. Each passes in and out of the arms, as if moving through a traffic wave, brightening the pattern, while within it then drifting into the quieter interarm regions where their light merges into the background. The arm's persistence comes from the density wave, a pattern in which gravity draws matter together more tightly than in surrounding areas, compressing gas clouds and setting off new cycles of star formation. It is a process that turns the galaxy's rotation into a kind of heartbeat, with each pass of the wave marking another pulse of creation. The pattern is rarely perfect. The arms may split or branch, forming spurs of starlight that extend into the interarm zones. Some of these spurs will fade quickly, dispersing into the larger disk, while others may grow into secondary arms, altering the overall symmetry. These irregularities are often born from encounters small satellite galaxies brushing past gas clouds, colliding at oblique angles, or subtle instabilities within the disk itself. In every case, the arms adjust, bending to accommodate the disturbance, folding the disruption into their ongoing rotation. The contrast between the arms and the interarm spaces is heightened by the different kinds of stars they contain. In the arms, young massive blue-white stars dominate, their brilliance short-lived but intense. In the interarm spaces, older and cooler stars spread their light more evenly, creating a softer amber glow. The dust lanes that run along the inner edges of the arms deepen this contrast, hiding newborn stars within their folds, until the wave carries them outward into clearer light. At wavelengths beyond the visible, the picture changes. In infrared, the dust itself glows softly, revealing the hidden structures of gas and molecules. In radio, the cold hydrogen that fills much of the disk can be traced, showing that the spiral arms are not just visual patterns, but genuine concentrations of material. These observations confirm what the density wave theory suggests, that the arms are sites of compression, their presence shaping both the appearance and the physics of the disk. The motion of stars within the arms reflects a balance of forces. Gravity pulls them toward the denser regions, but their orbital momentum carries them onward, ensuring that they do not remain trapped. Gas, being collisional, responds more directly to the compression, slowing more than the stars and thus experiencing greater density increases. This difference is crucial, for it is in the gas that star formation begins, and the delay between compression and ignition explains why the brightest clusters often lie just downstream of the densest dust lanes. Over time, the spiral pattern can shift. The speed at which the density wave moves relative to the stars, the pattern speed may slow, causing the arms to open more widely, or it may speed up, tightening their curves. This change can be driven by interactions, by the redistribution of mass within the galaxy, or by variations in the flow of gas from the halo. The irony is that while the spiral appears to be a stable feature, its geometry is always in quiet negotiation with the forces that sustain it. Occasionally, the arms may host particularly intense star-forming regions, giant molecular complexes that collapse into massive clusters and associations. These regions can shine so brightly that they dominate the appearance of an arm, their light visible from far beyond the galaxy itself. Yet even these luminous knots will eventually disperse their stars, spreading into the disk, their gas recycled into the next wave of formation. In this way, the spiral arms are less like permanent structures and more like travelling stages upon which the drama of starbirth and death is continually enacted. The interarm regions, though quieter, are not empty. Older stars wander here, their motions gradually mixing them into a diffuse background. Some were born in the arms and have since drifted away. Others may have formed in smaller bursts outside the main density waves. Gas in these regions is generally too thin for large-scale star formation, but isolated pockets can still collapse into stars, adding a few younger points of light to the otherwise mature population. The boundaries between arm and interarm are not fixed but constantly shifting, defined by the movement of the wave and the rotation of the galaxy. From above, the spiral pattern appears both precise and fluid, its curves smooth yet full of small deviations. The number of arms a galaxy displays is not immutable. Some systems have two grand well-defined arms, others several looser, flocculent ones. Changes in mass distribution, interaction history, and gas content can all alter this number over cosmic time. In the galaxy's present state, the arms are clear but not rigid, their flow continuous yet subtly reshaped, with each passing 100 million years. The persistence of the arms depends on the balance between gas inflow and star formation. If the supply of cold gas from the halo diminishes, the arms will gradually lose their brightness as new star formation declines. Without the contrast provided by young hot stars, the pattern will soften, eventually becoming little more than a faint modulation in the disk's overall light. For now, however, the inflow continues, feeding the arms and maintaining the spiral's clarity. Observations from great distances reveal other galaxies in similar states, their arms glowing with knots of star formation, their dust lanes dark against the light. Seen edge-on, the arms are hidden, the galaxy appearing as a thin glowing band bisected by a dark midplane of dust. Only from above or below does the full geometry become visible, the winding arcs stretching from the bulge into the outskirts. This perspective reveals the spiral's essential truth that it is not a rigid form, but a wave in matter, a pattern maintained by the collective motion of billions of stars and clouds. The arms may give the impression of permanence, but they are renewed with every passage, their shapes subtly rewritten by the interplay of gravity motion and the ceaseless birth and death of stars. In the quiet depths of cosmic time, this renewal is unhurried. The galaxy turns at a pace too slow for any single observer to witness change, yet over eons the pattern will evolve, responding to the shifts in its own mass and to the touch of the galaxies around it. For now, the arms remain distinct luminous against the dark lanes that thread between them, winding outward in a slow, deliberate grace that will hold for as long as the conditions of their creation endure. The spiral galaxy does not exist in isolation. Around it, the intergalactic environment is populated with smaller companions, dwarf galaxies, loose star clusters, and faint streams of gas, all moving through the same gravitational domain. Some of these companions are ancient, having orbited for billions of years, while others are recent arrivals drawn in along the filaments of the cosmic web. Their orbits are rarely smooth. Tidal forces from the main galaxy stretch and distort them, pulling out long tails of stars and gas that arc across space. These tidal streams, faint but coherent, are the lingering signatures of past interactions, some stretching far beyond the visible disk. Over time, many companions lose so much mass that they dissolve entirely their stars, dispersing into the halo, their gas stripped and funneled into the disk, where it can feed new star formation. Such infall events are quiet but transformative, each one adding material altering the disk's dynamics and subtly reshaping the spiral arms. A close pass by a more massive satellite can produce stronger effects. The gravitational tug may warp the disk, tilting its outer regions or pulling one arm into a looser curve than the other. In some cases, the companion's passage triggers a wave of star formation that sweeps through the arms, brightening them for tens of millions of years. These encounters do not erase the spiral pattern. Instead, they imprint it with unique asymmetries, small departures from perfect symmetry that make every galaxy's structure distinct. Gas from companions often arrives with different angular momentum than the disk's rotation, and when it settles it can create counter-rotating streams or rings. These features may persist for hundreds of millions of years, eventually mixing into the general rotation, but leaving a long-lasting mark on the chemical and kinematic structure of the disk. The inflow of such gas is vital to the spiral's survival. Without replenishment, the cold molecular gas in the arms would gradually be consumed, and star formation would slow to a faint trickle. The galaxy would still rotate, but its arms would lose contrast, fading into the smoother light of older stars. With each new addition of material, however, the arms are refreshed, the density waves strengthened, and the pattern sustained. In the outer disk, where the influence of the central bulge is weaker, the arms are more easily perturbed. Passing satellites or streams of infalling gas can induce flocculent patterns, short disconnected segments of spiral structure that overlay the main arms. These segments often host small bursts of star formation, lighting up regions that would otherwise remain dim. Though they lack the grand sweep of the primary arms, they add complexity to the disk's appearance and contribute to its ongoing renewal. The Halo 2 records these interactions. Stars torn from satellites trace vast looping paths, their distribution revealing the gravitational contours of the dark matter envelope. Some streams are relatively recent, still narrow and well-defined. Others are ancient, spread into diffuse shells that hint at mergers long past. Astronomers studying such features can reconstruct a galaxy's interaction history, reading its halo like an archive of orbital events. Even without direct collisions, the constant gravitational interplay between the spiral and its surroundings shapes its evolution. The galaxy's position within a larger group or cluster can influence the rate of gas infall, the frequency of satellite encounters, and the stability of its outer disk. In denser environments, high-speed encounters with other galaxies can strip gas from the outer regions, a process called ram pressure, reducing the material available for future star formation. In more isolated settings, the spiral may retain its gas for longer, sustaining its arms deeper into cosmic time. Interactions also affect the galaxy's rotation curve. The redistribution of mass during mergers and infall events can alter the balance between the disk bulge and halo, subtly changing the pattern speed of the spiral arms. Such changes are gradual, but over hundreds of millions of years they can tighten or loosen the arms, shift their pitch angles, and modify the spacing between them. The central bulge remains the most stable element through all of this, its dense population of old stars relatively untouched by the slow reshaping of the outer disk. It acts as a gravitational anchor, holding the inner ends of the arms firmly in place even as their outer reaches flex and bend. The bulge's composition continues to age its stars, moving steadily toward cooler temperatures and redder light. Only occasionally does gas driven inward by an interaction spark a small burst of new star formation at its edge, briefly adding younger stars to the mix before the activity fades again. The interarm regions respond differently to environmental changes. A satellite's passage or an inflow of gas may brighten one arm, altering the contrast with its neighbour, and making one side of the galaxy appear more prominent. Over time, this imbalance can shift with the brighter arm fading, as another strengthens the pattern, cycling slowly, in response to the changing flow of material. Dust lanes adjust to these changes as well, moving to follow the regions of greatest compression, marking the shifting front lines of star formation. From above, such alterations are subtle, noticeable only when comparing the galaxy's form across vast spans of time. To the stars themselves, these changes are imperceptible. They continue their orbits without awareness of the larger structures they help compose. From the perspective of the universe, the spiral's evolution is part of an ongoing exchange between galaxies, a transfer of matter, momentum, and structure that never truly stops. Each encounter, each stream of gas, each gradual merger adds another layer to the spiral's history. The arms may appear serene and unchanging to a single gaze, but they are in fact the result of a complex, constantly shifting balance of forces. In time, the accumulation of such events will alter the galaxy's identity entirely. The arms may become looser or more tightly wound, new ones may emerge while old ones fade, and the disk itself may grow thicker as stars are scattered out of the plane by repeated interactions. Yet for now the spiral remains whole, its arms winding outward in luminous arcs, each one a momentary expression of processes that began long before, and will continue long after the present pattern is gone. Around it the companions still orbit the streams, still flow, and the halo still holds everything in its unseen grasp. The galaxy moves through space not as an isolated island of light, but as a participant in a vast interconnected system, its beauty shaped as much by the space beyond its boundaries as by the matter within. It is in this constant dialogue with its surroundings that the spiral finds both its vulnerability and its longevity. In the heart of the galaxy, the central bulge glows with the combined light of billions of old stars, their orbits oriented in every direction, forming a dense spheroidal swarm. These stars are survivors from the galaxy's earliest age, forged in the chaotic mergers and collapses that shaped its foundation before the spiral arms ever emerged. Their colours are warm, their light steady, a golden counterpoint to the younger blue-white clusters scattered along the arms. Here star formation is minimal. The gas that once fueled it has long since been consumed or driven outward. The bulge is not silent, however. Its gravitational influence shapes the orbits of stars and gas throughout the inner disk, anchoring the spiral arms and stabilizing the galaxy's core. In many spirals, a supermassive black hole resides at the very center of the bulge. Though it is invisible directly, its presence is revealed through the rapid motion of stars and gas in its vicinity. Most of the time, such a black hole is quiescent, swallowing only a small trickle of matter and giving off little light. But occasionally gas is driven inward by interactions by bar-like structures in the disk, or by random instabilities, and when it falls toward the black hole it heats to extreme temperatures, emitting radiation that can briefly outshine the rest of the galaxy. In this galaxy's current era, the central black hole rests in near darkness, its influence felt more through gravity than through light. Around the bulge, a transition zone leads into the bright inner arms. Here the density of stars is high, and gas clouds are compressed by both the gravitational potential of the bulge and the passing density waves of the spiral. This combination makes the inner arms fertile grounds for star formation, producing clusters that shine brilliantly against the background. Dust lanes thread through these regions, their shapes curved by the orbital paths of the gas and stars. These lanes both hide and reveal. In visible light they appear as dark streaks, but in infrared they glow, tracing the warm birthplaces of stars. Some galaxies host a bar-shaped structure within this inner region, a linear arrangement of stars and gas stretching from one side of the bulge to the other. Such bars act as channels, funneling gas inward toward the central regions, sometimes feeding the black hole, sometimes fueling bursts of star formation near the bulge. Bars can form and dissolve over time, their longevity dependent on the distribution of mass and angular momentum within the disk. In this galaxy, a short bar has begun to take shape, its faint elongation altering the orbits of nearby stars. The development of such a feature is gradual, almost invisible on human timescales, yet it may influence the galaxy's structure for hundreds of millions of years. The bulge's role in the galaxy's life is both stabilizing and transformative. By anchoring the spiral pattern, it ensures that the arms maintain their connection to the center rather than drifting apart. At the same time, its gravitational pull can drive resonances within the disk, creating rings or gaps at specific radii, where stars and gas become concentrated or depleted. These resonances can subtly alter the brightness of the arms, changing the balance between them over time. The chemical composition of the bulge tells a story of rapid early star formation. Its stars are enriched in elements forged in supernovae, indicating that they formed from gas that had already been processed through multiple generations of massive stars. This enrichment means that any new stars forming here, rare though they are, would be born with a higher metallicity than those in the outer disk, affecting their color lifespan and potential to form planets. Yet for all its richness, the bulge is a relatively quiet place compared to the spiral arms. Its stars move in random paths, colliding only in terms of gravitational encounters that alter their orbits. The absence of large amounts of cold gas means that there is little of the turbulence and chaos that defines the arms. Instead, the bulge is a realm of slow change, its evolution measured in the gradual dimming of its oldest stars and the occasional infall of matter from the disk. Surrounding the bulge, the inner arms spiral outward in tight curves before opening into the broader arcs of the mid-disk. The transition between these regions is subtle, marked not by a sharp boundary, but by a gradual change in density and rotation speed. Here, the influence of the bulge begins to fade and the disk's own dynamics take precedence. Still, the gravitational connection remains. The bulge's mass shapes the orbital velocities even far out into the disk, keeping the rotation curve flat in combination with the dark matter halo. Occasionally, a burst of gas driven inward will ignite a ring of star formation near the edge of the bulge, creating a luminous band that circles the center like a necklace of light. Such rings are transient, fading within a few 100 million years as the gas is consumed or dispersed, but while they last, they add a distinctive feature to the galaxy's core. The interplay between bulge, disk and halo is one of quiet complexity. The bulge anchors the arms, the disk provides the rotating platform on which they form, and the halo holds everything together. Changes in any one of these components can ripple through the others, altering the galaxy's structure and behavior. For now, the balance holds. The bulge remains a dense golden heart at the galaxy's center, its ancient stars glowing steadily, its gravitational reach binding the spiral into coherence. Around it, the arms continue their slow luminous sweep, and beyond them the halo extends invisible but essential. From the perspective of a distant observer, the bulge might seem merely a bright spot at the galaxy's center, easily overlooked in favor of the sweeping arms. Yet without it, the spiral's elegance would unravel its pattern, loosening into disorder. In the stillness of cosmic time, the bulge is both a relic of the galaxy's birth and a guarantor of its present form, a quiet, unblinking eye at the center of a vast and turning storm of stars. Not all spiral galaxies share the same design. Some display two grand symmetric arms winding outward from the center in long, graceful curves, while others are flocculent, their disks mottled with many shorter fragmented arms. Between these extremes lie galaxies with mixed patterns, perhaps a dominant pair of arms near the core that split into multiple branches toward the outer disk. The form a spiral takes depends on a complex interplay of mass distribution, rotation, speed, gas content, and interaction history. In grand design spirals, the density waves are strong and coherent, often maintained by the gravitational influence of a central bar, or by resonances with the orbits of stars and gas. These arms are bright and well-defined, their dust lanes sharply trace their blue clusters, forming nearly continuous ribbons of light. In flocculent spirals, the density enhancements are weaker and more localized, arising from stochastic star formation rather than large-scale waves. The arms appear patchy, each segment short-lived, dissolving into the interarm regions within a few 100 million years. Yet despite their differences in appearance, both types are governed by the same fundamental mechanics of rotation gravity and the cycling of gas into stars and back again. The pitch angle of the arms, the measure of how tightly they wind, is also a key feature. Galaxies with faster rotation speeds or more massive central bulges often have tightly wound arms, while those with slower speeds or less central mass display looser spirals. The pitch angle can change over time as the galaxy evolves, influenced by shifts in mass distribution or by encounters with other galaxies. Even a minor interaction can subtly alter the arm's curvature, changing the overall geometry in ways that persist for billions of years. The contrast between arms and interarm regions is another point of variation. In some galaxies, the difference is stark. The arms are brilliant with young stars, and the spaces between are dim, populated mainly by older stars. In others, the contrast is softer, with star formation occurring more evenly across the disk. This balance depends on the amount and distribution of cold gas, the strength of the density wave, and the rate at which gas is replenished from the halo or from infalling companions. Observationally, the differences between spiral types are often clearer in certain wavelengths. In optical light, young stars dominate the arms, making them stand out vividly. In infrared, the older stellar population becomes more apparent, revealing that the underlying mass distribution is often smoother than the arm pattern suggests. In radio, the cold hydrogen gas outlines both arms and interarm regions, showing that the raw material for star formation is more widely spread than the visible light alone would indicate. Spiral structures can also host rings, circular features that form at resonances where the orbital motions of stars and gas match the pattern speed of the arms or a central bar. Inner rings often encircle the bulge, while outer rings can form near the edge of the visible disk. These rings may be sites of enhanced star formation, their gas compressed by the resonance into narrow, dense bands. Like the arms, they are not permanent. They can dissipate if the resonance conditions change. The number of arms in a spiral galaxy is not fixed over its lifetime. Interactions, changes in rotation speed, or variations in gas supply can cause arms to merge, split, or fade. A galaxy that once displayed 4 prominent arms might later settle into a 2-arm configuration, or vice versa. These shifts are gradual, occurring over hundreds of millions of years, and are rarely disruptive to the overall stability of the disk. In some cases, asymmetry becomes the dominant trait, with one arm longer, thicker, or more luminous than its counterpart. Such lopsidedness often results from tidal encounters, which can displace mass in the disk and alter the balance of the arms. Even after the immediate effects of an interaction fade, the asymmetry can persist, slowly evening out, only as the disk redistributes its mass. Some spirals develop extensions beyond their main disk. Tidal tail streams or plumes of stars and gas flung outward during close encounters. These features are more transient than the arms themselves, fading as their stars disperse into the halo or are reabsorbed by the disk. Yet while they last, they serve as visible records of a galaxy's more dynamic moments, connecting its present form to its history of encounters. The morphology of a spiral galaxy is thus a balance between order and irregularity, between the stable rotation that maintains its broad structure and the constant small perturbations that alter its details. The arms are never static. They are renewed with each passage of the density wave, their shapes subtly rewritten by the movement of matter. The differences among spirals across the universe, grand flocculent barred, tightly wound, loosely wound, are variations on a single theme, each shaped by local conditions and history. For the galaxy in focus, its current form is that of a moderately open, grand design spiral with 2 main arms emerging from the bulge and branching into several fainter segments in the outer disk. The pitch angle is wide enough to give the arms a graceful sweep, yet tight enough to maintain a strong connection to the central structure. Dust lanes curve along the inner edges of the arms, and bright knots of star formation punctuate their length. The interarm regions are populated by older stars, their light softer and redder, giving the galaxy's overall colour a subtle gradient from blue in the arms to gold near the centre. From above, the symmetry is evident but not perfect. One arm is slightly more luminous, perhaps the result of a recent minor interaction. In the outer disk, faint fragmented arms trace patterns in the cold, gas marking places where future star formation may ignite. These details will change in time, but the underlying rotation and gravitational balance will continue to support the spiral structure for billions of years to come. In this variety of forms, the spiral galaxy demonstrates the adaptability of structure in a dynamic universe. Its arms, whether bright and continuous or fragmented and diffuse, are temporary expressions of deeper enduring processes. The rotation of a disk in a gravitational field, the compression of gas into stars, and the recycling of matter through countless generations. Even when the exact pattern shifts, the principles that shape it remain, carrying the spiral form forward through cosmic time. Galactic encounters do not always end in violent mergers. More often they unfold as slow glancing interactions that leave both galaxies intact but altered. When another galaxy passes nearby, its gravity reaches across the void, tugging at the spiral's disk and arms. Even without direct contact, this pull can shift the orbits of stars and gas, creating tidal features, subtle elongations of the arms, faint outer loops or warps in the disk's plane. These distortions can persist for hundreds of millions of years, gradually winding into the disk or dissipating into the halo. The influence of such encounters depends on timing angle and relative mass. A small companion may simply pass by, drawing out a single arm slightly farther than its twin. A more substantial neighbour can induce large-scale asymmetries, increasing the contrast between arms or triggering flocculent segments in otherwise grand design spirals. In some cases, the gravitational shock sends waves of compression through the disk, igniting bursts of star formation that light up the arms in sudden, brilliant arcs. These episodes may last only tens of millions of years before fading, leaving behind clusters that drift into the interarm regions. While the stars remain, the heightened glow of the arm subsides, and the spiral settles back into a steadier rhythm. Interactions can also funnel gas inward toward the galaxy's center. The tidal forces rearrange orbital paths, causing some material to lose angular momentum and spiral toward the bulge. This inflow can fuel central starbursts or briefly feed the supermassive black hole, awakening it into an active phase. In such periods, jets or outflows may emerge from the galaxy's core, carrying energy and matter outward. These outflows can compress gas in the inner arms, triggering more star formation there. But they can also heat and disperse gas, slowing the pace of creation in certain regions. The overall impact is a complex balance of stimulation and suppression, varying with the scale and geometry of the encounter. Not all encounters are fleeting. Some companions become bound, orbiting the spiral for billions of years. With each pass, they draw out tidal streams and transfer material, gradually losing mass to the larger galaxy. The streams they leave behind form delicate arcs in the halo, looping far beyond the disk. Over time, the companion may dissolve entirely, its stars blending into the halo's smooth distribution, its gas feeding the spiral arms. In the disk itself, repeated tidal influences can shift the pitch angle of the arms, or alter their pattern speed, leading to gradual reconfiguration of the spiral structure. These changes are not sudden transformations but slow adjustments, written into the rotation over cosmic time. In rare cases, a near-equal mass encounter will lead to a full merger. Such events are transformative, often destroying the spiral pattern entirely. The stars of both galaxies are thrown into new orbits, forming a spheroidal system without arms. the gas compressed in vast shocks triggers an intense but short-lived burst of star formation, before much of it is either consumed or expelled. Yet even in these disruptive cases, the result is not random chaos but a new equilibrium, a different galactic form emerging from the collision. The spiral in focus here has avoided such a fate, so far passing through an environment that offers encounters rich enough to shape but not to destroy. Several small companions orbit in its halo, some trailing streams of stars, others still intact. A few have already been absorbed, their remnants visible only in faint overdensities of halo stars or subtle shifts in the disk's rotation. In the outer arms, low surface brightness features betray the imprint of past interactions. A faint plume curving away from one arm, a ripple in the star density near the disk's edge, a change in dust lane curvature that hints at past tidal stretching. From the perspective of the galaxy's stars, these changes are imperceptible, their orbits altered by only small amounts. Yet on the scale of the entire structure, such shifts accumulate, gradually shaping the spiral's identity. The intergalactic medium also plays a quiet role. Streams of gas stripped from other galaxies or drawn along filaments of the cosmic web sometimes pass close enough to be captured. These infalls replenish the galaxy's cold gas reservoir, extending the life of its arms by sustaining star formation. Occasionally the gas arrives with a different motion than the disk, setting up counter-rotating layers or rings. These mismatch flows can create turbulence where they meet, producing localized bursts of new stars that briefly brighten otherwise faint regions. Encounters can also alter the vertical structure of the disk. A passing companion may tilt the outer disk relative to the inner regions, creating a warp visible when the galaxy is seen edge-on. Such warps often oscillate, slowly flattening over time unless renewed by further interactions. In the meantime, they subtly change the paths of stars and gas, affecting the density and stability of the outer arms. The galaxy's central bulge, by contrast, remains largely immune to these disturbances. Its dense stellar population and strong gravitational binding keep it stable even as the disk around it flexes and shifts. This stability provides the inner anchor that allows the arms to adapt without losing coherence entirely. The halo too mediates the effects of encounters, absorbing some of the energy and redistributing mass in ways that reduce the risk of total disruption. Over the long term, the cumulative influence of many minor encounters can be as significant as a single major event. The spiral pattern may shift toward a looser or tighter, winding the number of arms may change, and the balance between star-forming and quiescent regions may adjust. The galaxy's history becomes a record of these interactions, written in the geometry of its arms, the streams in its halo, and the distribution of its gas. Yet for all this gradual change, the spiral retains its identity. Its arms still sweep outward from the bulge, its dust lanes still trace the paths of density waves, and its outer disk still glows with a faint light of older stars. The slow shaping by encounters is part of its life, a process as natural as the birth and death of stars within its arms. In the vast timeline of the universe, no spiral remains untouched, but those that endure are those that adapt, folding each new influence into the quiet rhythm of their rotation. The galaxy continues to turn its current form, a reflection of everything it has met and everything it has absorbed, its future already seeded with the possibilities of encounters yet to come. Star formation within the spiral arms is not uniform across the galaxy's lifetime. It rises and falls in cycles each lasting hundreds of millions of years, driven by the availability of cold gas and by the movement of density waves through the disk. When the arms are rich in molecular clouds, bursts of creation illuminate them with clusters of hot massive stars. These clusters, though dazzling, fade quickly. Their brightest members live only a few million years before ending in supernovae that scatter heavy elements into the interstellar medium. The explosions are both destructive and constructive, destroying nearby clouds while also sending shockwaves that compress other regions into new bursts of formation. Between these peaks of activity lie quieter periods when the gas supply thins. The arms still sweep through the disk, but with fewer luminous knots, their contrast against the interarm region softening. This rhythm gives the spiral a breathing pattern, phases of brilliance followed by intervals of calm. The overall trend is shaped by the inflow of fresh gas from the halo and by the gradual enrichment of the disk. Over billions of years, the metallicity of the gas increases, changing the cooling rates and the types of stars that form. Early in the galaxy's life, massive stars were more common, burning bright and short. Now, with higher metallicity, lower mass stars form more frequently, living longer, and contributing to a steady background of light that fills the interarm spaces. The arms themselves evolve as star formation waxes and wanes. In times of abundance, their shapes are sharpened by the brilliance of young stars, their dust lanes deepened by fresh inflows of material. In leaner periods, they grow more diffuse, their outlines less defined, their brightness, relying more on the older stars that remain within them. Yet the density waves persist regardless of these fluctuations, continuing to compress gas where it exists, and marking the disk with their spiral geometry. Star clusters within the arms range from small associations of a few dozen stars to massive complexes containing thousands. The largest clusters can survive for hundreds of millions of years, slowly dispersing into the field population of the disk. As they age, their colour shifts from blue to white to yellow, blending them into the older stellar background. Many stars that now wander the interarm regions were born in such clusters long ago, their origins written only in their motions and compositions. Some regions of the arms are dominated by giant molecular clouds, vast cold reservoirs of gas and dust, where star formation proceeds in dense knots, shielded from the surrounding radiation. These clouds are shaped by the spiral pattern, their elongated forms aligned with the dust lanes that mark the leading edge of the arms. Within them, gravitational collapse proceeds in layers. Small fragments form, first collapsing into protostars that begin to heat their surroundings, eventually clearing cavities in the clouds. Over time, the entire cloud is dispersed, its material either locked into stars or driven back into the interstellar medium. Supernovae, stellar winds, and radiation pressure all play roles in dispersal, ensuring that no single cloud remains intact for more than a few tens of millions of years. The feedback from massive stars is a key regulator of star formation in the galaxy. Without it, gas would collapse into stars too quickly, exhausting the supply and ending the cycle prematurely. With it, the process is self-limiting. Bursts of creation are followed by periods of dispersal, allowing gas to cool and recombine before the next wave arrives. This balance sustains the arms over long timescales, even as the total rate of star formation slowly declines. The interarm regions, though less active, are not entirely devoid of creation. Small pockets of gas occasionally collapse into stars, particularly where turbulent flows from the arms converge. These isolated events add to the diversity of the stellar population and maintain a subtle continuity between the arms and the spaces between them. Over time, stars drift from their birthplaces, their orbits, carrying them across the disk and erasing any simple boundary between arm and interarm. The chemical evolution of the disk mirrors the pattern of star formation. Each generation enriches the gas with heavier elements, which then become part of the next wave of stars. The inner disk, where star formation has been most intense for the longest time, shows the highest metallicities, while the outer disk remains more pristine. This gradient is visible in the colours of the stars and in the spectral lines of the gas, a quiet record of the galaxy's ongoing transformation. Observations in multiple wavelengths reveal the full scope of this cycle. In ultraviolet, the younger stars trace the most recent sites of creation. In visible light, the arms stand out with their blue clusters and dark dust lanes. In infrared, the older stars dominate, showing that the underlying mass distribution is smoother than the arms suggest. In radio, the hydrogen gas maps the potential for future star formation, extending even into regions where the arms fade from view. All these perspectives confirm that the spiral is not a static sculpture, but a living process, its structure maintained by the constant movement of matter and energy. The outer disk, though less dense, plays an essential role in this cycle. It acts as a reservoir holding gas that may one day be drawn inward by tidal interactions, spiral torques, or instabilities in the rotation. When such inflows occur, they can revive flagging arms, triggering fresh bursts of star formation, even in a galaxy entering a quieter phase. In this way, the outer disk and halo serve as the spiral's long-term supply lines, linking its future to the broader flows of matter in the universe. Within the arms, life cycles continue without pause. Stars are born, live their varied spans, and return their matter to the medium from which they came. Dust forms in the atmospheres of dying stars, is dispersed into the interstellar medium, and is eventually incorporated into new molecular clouds. The metals forged in supernova seed future stars and planets, increasing the complexity of matter with each cycle. The spiral pattern is the stage upon which all this unfolds, a pattern, both delicate and enduring, shaped by forces that care nothing for the details of individual lives, yet produce in their slow work a form of lasting beauty. Even as the galaxy ages and its total star formation rate declines, the arms remain as visible reminders of its ongoing vitality, their light a composite of countless stellar stories written across cosmic time. Gas flows within the galaxy's disk follow paths set by both gravity and rotation, and these flows are essential to the maintenance of the spiral arms. Cold hydrogen drifts inward along the dust lanes that mark the leading edges of the arms, compressed as it enters the denser regions of the density wave. This inflow feeds the cycle of star formation, but it is not evenly distributed. Some arms receive more gas than others, leading to differences in brightness and structure across the disk. The origin of this gas is varied. Some is recycled material from dying stars returned to the interstellar medium through winds and supernovae. Some arrives from the galaxy's outskirts, pulled inward by gravitational instabilities, or by torques from the spiral pattern itself. And some comes from beyond the disk, entirely funneled in through the halo via filaments of the cosmic web, or stripped from smaller companions. Each source has its own chemical signature mixing to form the complex composition of the disk's gas. The motion of gas is shaped by the galaxy's rotation curve. Because the rotation speed remains nearly constant with radius, a result of the dark matter halo's gravitational influence, gas streams do not spiral rapidly inward or outward. Instead, they follow elongated orbits, slowly drifting relative to the density wave. This motion means that gas can spend millions of years within an arm before moving on, allowing ample time for clouds to collapse and form stars. Yet the process is far from uniform. Turbulence within the interstellar medium creates variations in density and temperature, producing a patchwork of active and inactive regions along the same arm. Large-scale flows are further complicated by feedback from star formation. Massive stars inject energy into their surroundings through winds and radiation, and when they explode as supernovae, they send shock waves that can accelerate or redirect gas. Some of this feedback drives matter out of the disk entirely, forming fountains that rise above the galactic plane before cooling and raining back down. These vertical motions enrich the halo with heavy elements, while also redistributing gas within the disk. On rare occasions, strong feedback can carve superbubbles hundreds of light-years across, clearing large cavities in the interstellar medium. These voids can disrupt the continuity of an arm, though the density wave eventually draws new gas into the gap. The interplay between inflow star formation and feedback is a self-regulating system. If star formation becomes too intense in a given region, feedback disperses the gas, halting further creation until fresh material arrives. If the rate falls too low, gas accumulates until conditions trigger a new burst. This balance keeps the arms active over long timescales, preventing the rapid consumption of the galaxy's fuel. In the inner disk, gas flows are influenced by the gravitational pull of the bulge, and in some galaxies by a central bar. Bars can act as conveyors, channeling gas inward toward the central regions, where it can form stars or feed the supermassive black hole. This inward transport can create rings of star formation near the bulge, bright and short-lived, that contrast with the more extended patterns of the arms. In the absence of a strong bar, gas tends to follow smoother paths, spiraling gently inward over billions of years. The outer disk operates under different conditions. Here the gas density is lower, and the influence of the spiral pattern is weaker. Star formation is less frequent, but when it occurs it can produce surprisingly large associations, as the available gas collects into a few massive clouds rather than many smaller ones. The outer regions are also more sensitive to external influences. A passing satellite or a stream of infalling gas can trigger waves that travel inward, subtly reshaping the arms as they propagate. The vertical structure of gas in the disk is layered. The densest, coldest molecular clouds lie close to the midplane where they're shielded from disruptive forces. Surrounding them is a layer of warmer atomic hydrogen, more diffuse, but still participating in the general rotation. Above and below this layer stretches a halo of hot, ionized gas, tenuous yet extensive, marking the interface between the disk and the galaxy's larger halo. This stratification plays a role in regulating star formation, as only the coldest gas can collapse into new stars. Chemical gradients in the gas mirror those in the stars with higher metallicities toward the center and more pristine compositions at the edges. These gradients are smoothed over time by radial flows, gas migrating inward or outward along the disk, but they never disappear entirely. Inflow from the halo can steepen the gradient if the accreted material is metal poor, while outflows can flatten it by removing enriched gas from the central regions. Observations of other spirals show that these processes are universal, though their balance varies. Some galaxies show strong inflow, fueling bright, well-defined arms. Others appear starved, their arms faint and dusty, the gas stretched thin across the disk. The galaxy here stands in the middle ground, neither in a starburst phase nor in decline, its arms sustained by a steady but modest flow of material. The role of gas dynamics in maintaining the spiral pattern cannot be overstated. Without the constant movement of matter through the arms, the density waves would leave no visible mark, and the disk would fade into a featureless expanse of aging stars. The arms exist because gas can be compressed, because stars can form, and because feedback can regulate the cycle without exhausting the supply too quickly. Even the smallest flows from a disrupted satellite from the halo from the galaxy's own outer disk contribute to the balance. Over the next billion years, these processes will continue to shape the spiral's appearance. Inflows may strengthen one arm while leaving another to fade. Interactions may trigger bursts in specific regions, and gradual shifts in the rotation curve may alter the arm's pitch angles. Yet the essential mechanics will remain the same: gas moving under gravity, compressed by patterns in the disk, forming stars whose light makes the spiral visible across millions of light years. In this way, the arms are less a structure than a consequence, an emergent feature of deeper flows and forces that will persist as long as the galaxy has matter to move and time to turn. Over time, even the most luminous spiral arms begin to fade. The change is not sudden. It unfolds over billions of years as the galaxy's reservoirs of cold gas slowly diminish. Star formation, once vibrant along the arms, becomes patchier, confined to fewer regions where enough dense material remains to collapse into new stars. The blue-white glow of massive young clusters gives way to the steadier, warmer light of older stellar populations. The arms retain their shape for a time, traced by the density wave, but their contrast against the interarm regions lessens, and the spiral pattern becomes a subtler modulation in the disk's overall brightness. The cause of this decline is simple. Star formation consumes gas faster than it can be replenished. Inflows from the halo and from interactions with smaller companions slow as the galaxy's environment changes. The cosmic web that once fed it directly has thinned, and the smaller galaxies within its gravitational reach have already been absorbed or stripped of their gas. Without fresh supply, the interstellar medium becomes increasingly enriched with heavy elements, but increasingly poor in mass, reducing the cooling efficiency needed for the formation of molecular clouds. The decline is not uniform across the disk. The inner regions, where gas density was always higher, maintain pockets of activity longer than the outskirts. In some spirals, a residual ring of star formation persists around the bulge, fueled by slow inward flows from the remaining gas in the arms. The outer disk, by contrast, becomes quiescent earlier its once active segments, fading into diffuse streams of older stars. Dust lanes remain but grow thinner, their darkness more the result of contrast against dimmer surroundings than of actual density. The density wave itself may persist for some time, even without strong star formation to highlight it. In this phase, the spiral arms appear in the light of older stars, visible more clearly in infrared than in optical wavelengths. The pattern becomes ghost-like, a structural memory of more active times. Over hundreds of millions of years, even this stellar contrast may soften, as orbital mixing smooths the distribution of stars across the disk. Some galaxies in this stage take on the lenticular form S0 galaxies, where a disk remains but without prominent arms. Star formation has largely ceased, and the galaxy's light comes from a population of stars that is aging together, gradually shifting toward redder wavelengths. Such transformations are common in galaxy clusters, where interactions and the hot intracluster medium strip away the last of a spiral's gas. In more isolated environments, the process is slower driven, mainly by the steady consumption of fuel and the lack of replenishment. The central bulge remains a dense and luminous core throughout this transition, though its population also ages. Without fresh gas inflows, it forms few new stars, and its light slowly shifts toward deeper golds and reds. The supermassive black hole at its center grows only marginally during this period, fed occasionally by the rare inward drift of gas, or by the infall of a small gas-rich companion. In the absence of such events, it remains dormant, exerting its influence only through gravity. The halo still surrounds the galaxy, but its ability to provide new material has diminished. Most of its gas is now hot and diffuse, unable to cool efficiently into the cold flows that once fed the disk. Tidal streams from long-ago mergers persist as faint elongated structures, gradually dispersing into the halo's smooth background. These relics mark the galaxy's more active past, when interactions were frequent and transformative. Despite the fading of the arms, the disk retains its rotation, the flat velocity curve preserved by the enduring presence of the dark matter halo. The stars continue their orbits, maintaining the galaxy's overall shape, even as its visible features change. From afar, such a galaxy might appear as a smooth, featureless lens of light, its spiral heritage detectable only through careful analysis of its stellar motions and mass distribution. In this quieter phase, evolution is dominated by slow internal processes. Dynamical heating caused by the cumulative gravitational influence of stars and remnants passing near one another gradually thickens the disk, Stars are scattered into higher orbits above and below the galactic plane, softening the sharpness of the disk's edge when viewed from the side. Over billions of years, the once thin spiral can become a puffier, more spheroidal system, even without any major mergers. The chemical evolution of the galaxy slows as well. With star formation, the recycling of heavy elements into new generations becomes less frequent. The metallicity of the remaining gas may be high, but its total mass is too small to significantly alter the composition of the existing stellar population. The galaxy's colour continues to redden as the brightest, bluest stars die and are not replaced. Occasionally, a fresh infusion of gas from an external source can briefly revive the arms. A small gas-rich dwarf galaxy might fall into the spiral's halo, its material stripped and added to the disk. Such an event can trigger a limited starburst, briefly re-illuminating parts of the arms. However, these episodes are usually short-lived and localized, fading within a few 100 million years as the new gas is consumed. In some cases, these revivals are enough to maintain faint arm structures for longer, delaying the full transition to a lenticular state. In the broader cosmic context, the fading of spiral arms is a natural step in galactic evolution. The universe's supply of cold gas is finite and was more abundant in its earlier epochs. As galaxies age, the processes that sustain their active phases, steady inflows, frequent mergers, and abundant companions become less common. The spiral phase, while long-lived, is not permanent. It is a chapter in a galaxy's life bracketed by a more chaotic youth and a calmer, quieter maturity. Yet even in decline, there is a certain beauty to the fading spiral. The arms, though dim, still trace the paths where countless stars were born. The disk, though less active, still carries the rotation and structure imprinted over billions of years, and the bulge with its dense core of ancient stars continues to shine a beacon of stability in a system that has moved from youth into age. In this way, the fading of the spiral is not an ending, but a transformation, the slow reshaping of form and light under the unhurried hand of time. The galaxy remains its structure intact, its motion steady, its history written in the distribution of its stars and the ghostly patterns of its arms. In the far future of the spiral galaxy, the last vestiges of its once bright arms become difficult to trace. The density wave pattern that had for billions of years organized the gas into luminous arcs still leaves a faint imprint in the stellar distribution. But without the illumination of massive short-lived stars, the arms blur into the broader light of the disk. The galaxy's colour has shifted decisively toward red and gold, its blue-white clusters long since faded. Star formation has not ceased entirely. Small clouds of molecular gas remain in the inner disk and near the bulge, sustaining a trickle of new stars, but the scale is tiny compared to its peak. The interstellar medium is thin and patchy, enriched with heavy elements from countless generations of stars, yet too sparse to sustain large-scale creation. In this quiet phase, most of the activity is slow redistribution. Stars continue their orbits, some migrating outward or inward through resonant interactions with what remains of the spiral pattern, or with lingering bar-like structures in the central regions. These radial migrations subtly alter the metallicity gradients of the disk, smoothing differences that had persisted for billions of years. Over even longer spans, the disk thickens further as stellar encounters and the influence of past mergers heat the orbits, blurring the separation between thin and thick disk components. The halo still surrounds the galaxy, vast and unseen, holding the mass distribution steady. Its streams of stars, remnants of long-absorbed companions, are now faint, stretched and diluted into near invisibility. Gas in the halo is predominantly hot and diffuse, unable to cool effectively without external compression. Occasional high-velocity clouds may still fall inward, but their effect on the galaxy's overall state is negligible. The cosmic web itself has become quieter. The flow of matter into the galaxy is slower than at any point in its history. The bulge, ever luminous, is now a deep golden sphere at the galaxy's heart, its population almost entirely ancient. The supermassive black hole at its centre remains, having grown incrementally from rare infalls over the aeons, but it is quiescent, its accretion disk thin and dim. The bulge's gravitational influence still shapes the orbits of the inner disk, yet without the bright traces of young stars, the inner spiral arms have softened into mere gradients of stellar density. From a great distance, the galaxy resembles a lenticular form, a smooth, featureless disk around a bright core, its once dramatic arms discernible only to careful analysis of stellar motion. The transformation has been gradual, a quiet aging rather than a sudden loss. The galaxy is still massive, still coherent, still turning under the pull of its own gravity and the vast halo beyond, but it is no longer in the active middle stage of a spiral's life. It has crossed into a slower era, its future changes driven by internal dynamics and rare external events. In deep time it may still encounter another large galaxy, and if so, the result will likely be a merger that erases the disk entirely, scattering its stars into a spheroidal form. If such a meeting never comes, the galaxy will continue to rotate in its lenticular state, slowly reddening as its remaining stars age, and no new bright populations arise to replace them. Even in this quiet form, the memory of its spiral past is embedded in its structure. The distribution of stellar orbits still reflects the pattern set by the density waves. The metallicity gradients still trace the history of inflow and star formation. The thickened disk still carries the marks of past interactions. The galaxy's halo, though invisible, is a vast archive of its growth, each faint star stream a record of a merger or encounter that once altered the disk. The interstellar medium, though reduced, still contains dust grains forged in dying stars long ago, circulating slowly through the aging system. This dust is no longer the seedbed for large bursts of star formation, but a remnant of a more active epoch, a fine haze drifting between older stars. The galaxy's light now comes predominantly from long-lived low-mass stars. Red dwarfs, nearly eternal on human timescales, dominate the population, their steady glow providing a background against which the remaining giants and subgiants stand out. Occasional planetary nebulae mark the deaths of intermediate mass stars, brief flashes of colour in an otherwise muted palette. White dwarfs accumulate cooling slowly over billions of years, their faint light a final whisper from stars that once burned brightly in the spiral arms. From within, the galaxy's night sky is different from what it was in its youth. The blue-rich fields of the arms are gone, replaced by a more uniform scattering of redder stars. The dust lanes are faint and sparse, their silhouettes less striking against the background light. The sense of structure is weaker. The grandeur of the spiral pattern is no longer an obvious presence, but a hidden order, detectable only through careful mapping of stellar positions and velocities. In the cosmic scale of things, this stage is not an end so much as a slow unwinding. The processes that built the spiral have run their course, and the galaxy has settled into a long, stable adulthood. It will remain luminous for trillions of years, even as individual stars age and fade, because the red dwarfs that now dominate will burn slowly and steadily for epochs beyond the age of the current universe. Long after the last trace of its arms has blended into the disk, the galaxy will still shine its light, crossing the expanding darkness to reach whatever observers may exist in the far future. This transformation from bright spiral to quiet lenticular is a testament to the timescales on which galaxies live. The arms that once wound outward in arcs of blue light were never fixed structures but patterns in motion, reliant on the flow of gas and the cycle of star birth and death. When those flows slowed, the patterns faded not in catastrophe, but in a gradual shift that left the galaxy intact, changed in form but still whole. Its history is written not just in its current appearance, but in the distribution of its stars, the chemistry of its gas, and the faint signatures in its halo. Even in stillness, it remains a product of motion shaped by the same forces that once drew light into spirals. In the quiet reaches of cosmic time, it continues to turn a remnant of an era when spiral arms were common and the universe was richer in cold gas. Now it is one of the elder systems, its beauty subtle, its energy muted, yet still a participant in the slow dance of structure across the cosmos.